Okay, good afternoon. The idea now is to show you my examples or my solutions to the examples that you had to model. One important thing is that these are only my solutions. It doesn't mean that it has to be exactly like this. When you are modeling, sometimes you have the possibility to do things in different ways. So most probably, some of you will have done things differently. Um, Not better or worse than my solutions. My idea is also to illustrate some things that maybe were not strictly necessary. So in some of the models, there are things that I added to for verification or to illustrate other points. And we start with the career mixer. Uh, uh, from what I've seen, most of you that uploaded your solution did it quite well. So I will go more or less fast. And if you want me to explain something further, please just ask. So the idea here is that we have the students who arrive to the event. Uh, we have a generator, we have a prototype entity that is the student, we have a distribution for the inter-arrival time, and then we are generating students with this with this random variable. The first thing they do is they spend an amount of time with the tagging. They don't have to queue for that. They spend some time, but there is no server. They can do it in parallel or whatever. We have a distribution for the time for the tagging that is uniform, and after that, some students go wandering. That is. They are not going to the stands, to the recruiters, and they spend an amount of time that is distributed with a triangular distribution, the time that they are spent in this part. And after that, most of them go to the recruiters, but some of them go to decide to abandon. Here I put a delay with a 0 time delay for the ones who abandon, with the idea to count the number of students who go through this delay to just to know. Okay, in this case, like in this one, the distribution, the decision to wander or not, the decision to abandon or not, are based on a discrete probability. So we have a distribution that says the values go to 1 or go to 2. In this case, abandon or go on, and the probabilities: 10% go on, abandon, 90% abandon. Sorry, go on. Then and here there will be, this will be the most interesting part. Here we have the recruiters, and in this model, what I did is that if we have 2 recruiters, I have 2 servers. If I have 3 recruiters, I have 3 servers, and all of them, their waiting queue is the same. So this one, the waiting queue is this one, is that one. So we can show it with the arrows, and the same this one. Okay, this is an easy way to model a multiple server. So we have only one queue, but when one of the servers is free, is idle, then gets the next one in the queue, or well, the next one, if the queue has priorities or whatever, gets the following one. This is not very convenient if we want to make models with different numbers. If we wanted to study different scenarios with different numbers of recruiters and so on, because each time we would need to add another server and so on. So there will be better ways to do that, but this is quite an easy one. Since in this case the service time is the same for both recruiters, I only need to put one distribution, and both servers, the service time is got from the same distribution. Okay, they go to this stand, then they go to this other one, and here it comes the part where I want to get some statistics. So the students go to a place, in this case a branch, and in this branch I want to classify them depending if they were they have been wandering or not, to have different numbers. In this branch how I classify the students as focused or wanderers. What I decided in this case is to deduce that from the things that they were doing, and this is quite practical in general. So you can assign states to the entities that are flowing in the system, and then these states will be recorded, and the time spent in each of the states will be recorded. In this case, I was doing that. I didn't mention, but I was doing that. For instance, when they are tagging, I say that they are tagging. When they are wandering, I say they are wandering. When they are here or here, in both cases, they are waiting. When they are here or here or here, they are being attended, and so on. And now in this branch, what I do is the choice to go to one statistics or the other is if the time they were attended was greater than 0. So the ones who were 0 time being attended are the ones who abandoned it. Then if it is greater than 0, then if the time they were wandering is greater than 0, these are the wanderers, then they go to 2. If they attended but not wandered, they are the focus, they go to 3. And if they didn't attend, they go to 1. So I have the different outcomes from this branch, and they go to this statistics, that is an statistics for the total time they were in the, if they were wanderers. Here the total time of the students if they were focused. And here in this one, it is the total time for all the students. So every student goes through these statistics, even those that abandoned, and so I get the total time, and then with the total time that I take samples of the total time of each student, and then when I finish the simulation, I will be able to see the minimum, maximum, average, or whatever. This is the idea with the statistics. Okay, right. And there is only one more thing here to comment. That is this is quite possibly you will have done this in many different ways. How to count the number of students that are in the event. And I have seen, I remember some cases where someone put an statistics, and when the student goes here, then it samples the number of students that are within the system at that moment. But we are getting samples just in the each time that a student is about to leave. We could do that in several times, and this would be a good approximation. But and it's quite sensible to do that. But what I try to do is to do it very precise. So when a student arrives, what I do is I duplicate the student and leave it in this queue, and then the student goes on, and when the student finishes, goes to this queue, and here this is a duplicate and a combine. So here in this queue, I will have one entity for each student that is somewhere here. So the way to know how many students I have in the system is just the average number of students in this queue, right? For this example, I don't need to match the students that are represented here as like a shadow. They are logged in the system, and when they exit, they get their log and they abandon. It was not necessary, but I did it because it is nice to illustrate. So what I did is when a student arrives, I here in the generator, I had a number that is the identity, and then I increase the identity by 1 and assign the current identity to the student, and so on and so on. So each student will have a number, 1, 2, 3, 4, 5, and so on. When I duplicate here I will have the entities with the numbers, and when the student finishes, very possibly the first student doesn't finish the first one because maybe the first student wanders and the second student is focused or whatever. But when the student arrives here, I want to that student to remove his or her tag. And the way to do that, that is what you usually do with combine and duplicate, is here in the combine, I require matching, and in the queues, I specify that the matching value is, in this case, the attribute identity of the student, right? And then they finish. Okay, so I simulated like in real time, more or less slowly. I will remove the arrows. And I have students wandering, students being attended in the queues. This is the number of students that I have in the system. I have finished. This time I have done a simulation of 6 hours. When I configured the simulation, I said that I was going to simulate 6 hours. So at the end, I have some students who are still in the system, right? For instance, I have a student, this one is a student 148, and this student 156. They are here 126. Here they are ordered, but where is one student 126? I don't know. Here maybe. Well, this is very. I was very lucky. I didn't know where that student was, but was here. And here is the student. Sorry, this is not a student. This is the wandering student 161, etc., etc. Okay. Okay. So for this model, the figures, for instance, the utilization. Each one of these servers has a different utilization. This has been utilized for 67% of the time, and this one 47% of the time. This doesn't make any difference because they are indistinguishable. I have put 2 servers, but it is just by the tool that one is more utilized than the other, but it's not meaningful. So the utilization, what I did is just the average of the 2, and the same with these 3 and so on. And one of the things that I did for verification in this case was to apply the little law, and I computed what I did in the little law, it was the difference between the number of students computed applying the law with the rate of student arrivals and the time they spent in the system, and the number of students that I have obtained directly. And they are not exactly the same, but very close to 0. So the difference between the number of students computed with the little law and with the unobserved is very similar. Okay, so this is a kind of verification. I am not losing a student somewhere or whatever, right? We will see later that in a different situation, when we don't leave students in the system, this will be exactly 0. Okay, so here is the model. I will explain the way to simulate the system working until the last student finishes. But now I will, what I want to do is to show you different ways of modeling the multiple servers. And one of the ways to do that I think many of you, many of you have done is, and it is very sensible, is using the entity processor. The entity processor, we can say we have 2 units. The capacity is 2 or 3 or 4 or whatever, and then it models. It is like is very similar to the other system. It is I get one recruiter, then I spend some time, then I leave the recruiter, and I say the capacity, the number of recruiters that I have. Okay, so this probably is what most of you have done. I don't know if it is the case. If you, well, it's quite difficult to make the reactions, but if you, for instance, are besides making questions, if you are understanding it well, or you find that this is what happened to you, you can make some emoticons or whatever. So Probably you have done this, and the problem is that very possibly if we simulate this, I'm simulating it slowly again. It doesn't. It's so short that it's better to see it moving. Okay, very similar to the previous case. If you have seen the utilization of these entities, that is here, somewhere here, the utilization, it says that is 73% and this is 83%. And if you have done in the other way, if you remember, they were lower. Here, they were 57 and 68. What is the problem? Or what was the problem? The problem was that utilization of this means that it is working, and it doesn't distinguish if it is working 1, 2, 3, all of the units at the same time. This is not what we want. We would really want to know the number of units that are in use in average. And what happens is that it was not in the 2025 one version, that is probably the one that you are using. I realized that when I was preparing this example, so I told JaamSim people that it would be interesting to have this the number of units in average use in average, because it is very close to a resource, and they added it in, and it is now in version 200 2025-04. The 2 and 3 skip them because they were committing some side effects and they had some problems. So if you get all the examples that I am showing you are already in the Moodle course. So if you want, you can take my models, you can execute them. But if you are using an older version, here you will have an error. Okay. And this for the use of the entity processors. But what can you do if, as in this case, it is not this is to illustrate the different ways of modeling things. You are not satisfied with the entity processor. You are not satisfied with putting several servers, and then but you want to do something that is general, so the number of recruiters is a parameter, but you don't have any entity in JaamSim that does that. One thing is make your own entity, make programming. It is open source, but it is difficult. The other one is try to find a way to solve things. And in this case, what I did is just make the model that I have a number of recruiters, a resource, that this is then more or less, this is the entity processor, but all in a submodel. So I made a submodel, the number of recruiters, I get a recruiter, then I spend some time, then I release the recruiter. Okay, and in this submodel, I have the time that they are waiting in the queue, the average number in the queue, the average time they are working, the occupation of the utilization, the average number of recruiters that I'm using, etc. So this is something that you can do. This is very general way of modeling servers. In this case, it shouldn't be necessary. It's better to use the entity processor once you have the possibility to see the number of the units in use in average. Okay, but in other cases, this is necessary, because in other cases, you are not getting a resource, spending sometimes releasing the resource, but it's quite frequent that you have get a resource, spend some time, and then when some condition is fulfilled, for instance, the next resource is free or whatever, then I release. So from this construct, you can model, with this construct, you can model more general things. That in this case, that is the server does the work, and at the end, the entity is released. Okay. Well, this is one thing, and okay, I will not simulate yet. Here I will show the other question, that is how to simulate more than the 6 hours. What do I do? First, I have to stop the arrival of students after the 6 hours. So I need a clock that says that the 6 hours have passed to close the arrival of students. In this case, I do it with a time series. I say that from 0 hours the value is 1. After 6 hours, the value is 0. And in this case, I don't put a cycle time because I'm not going to, I'm going to make a single simulation. But in other cases, you have a system that is open some hours in the day. So 0, 1, then you cycle each day or each week or whatever. And this time series, here in an expression threshold, what I do is that the open condition is that the present value of the time series. So it is open when it is 1, it is closed when it is 0. So it is open only from 0 hours to 6 hours, right? And in this entity, in the generator, in thresholds, I say that the threshold list in this case is this expression threshold, the open. What it does, if you put the help, is when the thresholds are satisfied, this is working, and when they are not satisfied, it stops immediately. There are different ways it stops. For this case, it doesn't make sense to other options, but in a server, sometimes what it does is when you close the threshold, then you finish the work you were doing and then you release, or many other options. There are lots of things that when you are doing a particular model, you have to investigate in the manual or whatever. But in this case, it is enough, okay? Right, so it doesn't stop. So now, how long should I simulate? 1 day, okay? Probably some minutes after 6 hours. How many? So the way to do it without problems is in simulation, I can put a condition to stop, a post condition. And in this case, the condition is, okay, that I don't have any student in the system and the 6 hours have passed, because maybe by chance after 3 hours, in a moment, there are no students. It could be. So the condition to post is that we are not in open time. Well, I can write it like this, equal to 0, or like this. It is not true that the open time is actually is now. And then I have no students in the system. And where can be the students? They can be wandering, so no students wandering in progress. They can be being attended, and in one station and in the other. And maybe you will say, okay, they could be also in the queues, but you say, okay, if they are in the queue, is because someone is being attended. So just I only need to put that they are being attended. Okay. So now I simulate instead, and I say when the post conditions is satisfied, then exit, finish. So now I leave the run duration, here is a 1 year or whatever, it doesn't matter. And when I simulate, they move, this is open. After a while, there will be the 6 hours. It closes and I finish with the students. And once I finish with the students, now the little law checking, it is exact, because all the students who enter have exited and so on. It's like a kind of balance, right? So this is for the model. I have explained how to have the average number of students with the little law, or the other way, or maybe you did it sampling the value in different, when a student is going to abandon, and the difference will be small. The utilization of recruiters, I have discussed how to do it correctly. If you are doing it with the entity processors, the number of students waiting is in the queues. The waiting time of students is the average queue times in the queues. And the total time spent, well, these are the statistics that I was explaining. In each one of the statistics, I was sampling the total time of each of the students, and then I can have the averages and so on. And it said, okay, make a model, estimate the statistics, and well, here, try in parentheses, try to reduce the uncertainty of the results below 5%. Okay, well, and the thing with the 6 hours and so on. Let's go with this uncertainty issue. To collect the results in the simulation, in run output list, you have put all the values that, here, all the things that you want to record, okay? So if you do a lot of simulations, you will have these values several times. For instance, just not, it's quite quick doing that, but one moment, it's not here. One moment, I have to find the solution just not to make it again. Well, I can make it again, why not? Let's do it. Simulation, multiple runs. I will make 100 replications, okay? So I will simulate 100 times this system. So I put no real time, so it is faster. I simulate, okay, I have finished with 100 simulations. I said it is quite easy, quite fast. Okay, open. Okay, now it is all right. 100 replications, and I have this average number and this the confidence interval. They will explain this later, but just to show it, the confidence interval is from this number to this plus this, or this minus this. So this is the uncertainty. And if I make the computation with this, for instance, it is 6%. And in other, if I do the same computation for the different values, some of them are 1%, another ones 1%, whatever. And another ones, maybe this one, nearly 4, this is nearly 10, okay? So two observations. Some of the variables are easier to estimate. You estimate them more precisely, and others less. One way to improve the estimations is to make more replications, okay? And in this case, I will just do one try. I will go, since it is quite fast, I will do 1000. If you want to go faster, then you hide the things that move, and there are others. Okay, it's fast enough. So, okay, I have finished. And now with 1000, for instance, now, sorry. I think it was greater than 5 before, and now it is less. And this is much less, and so on. So this would be more or less the way to improve the results. And here, one point, I have just done 100, 1000 in this case. If you do it if you make an analysis, it is possible that and you plot the results with more replications, you have narrower confidence intervals. It is possible. The typical thing is that it starts high and then very quickly it drops down, and then it more or less stabilizes or goes down more slowly. It is possible that after many it stabilizes in a value that is higher than what you expected. Okay, maybe it is impossible to have such a precision with the number with the simulation, and you should say that I can estimate this value with this confidence, with this precision, but no more. All right. But in general, the idea is that if you do too few replications, you will get very uncertain values, and if you do more, they will be more and more certain. This is something that will be explained later in the part of the analysis, but I wanted just to show it in this example because that was in between parentheses, but there was a question about that. Okay, right. Let's move to another example, and here you have different examples depending on your ID, and I will start with the machine failure and repair, and this is we have 20 because it's more different to others. We have 25 machines, and after they have some time between failures, so after some time they fail, and they are repaired by there are 6 technicians repairing. If some of the technicians is idle, is free, will repair with a service time, a repair time, and if the 6 of them are busy, then you have to queue and so on. So the strange thing in this case is that I don't have an arrival of machines in the time, but the most natural way to see this is that I have 25 machines and they are somehow cycling. They are working, then they fail, they are being repaired, they go working again and again and again. So I would reflect this in the model. And here in the model, I generate at the beginning 25 machines immediately, and then they go to a delay. And here I have the 25 machines, and they spend some time. That is the time between failures. So the time here, the time they spend here is the time between failures. That is this distribution. That is an exponential. When they finish, they get a resource. Here again, I modeled this that could be done with an entity processor, but again, I did it with a resource to have the average number of repair people. Then if there is a resource free, they get the resource, and then they spend an amount of time, and then they release the resource. And then I compute the statistics because I want the statistics of the repair times, the time between failures, and so on. And here the difficulty, one of the difficulties is that if I do the state thing, so here when I am here, I am working, and when I am here, I am being repaired, and when I am here, I am waiting. The problem is that the same machine goes and goes and goes, so it accumulates. So there are 2 options. One is that each time that a machine fails, I count it with an assign. The other way, what I did in this case, is that when a machine fails, I record the time, and then I say that the wait time is 0, the repair time is 0. And then after the waiting time, when it finishes waiting, then I compute how long it was waiting this time. Then when it finishes being repaired, I compute the time from the current time and the last time, the time it has been being repaired, so I can make the statistics of queuing time or repair time, right? But this is one of the ways, only one of the ways. Right. Here again, there is one way to compute the number of times that are down at some point as the ones that are here in the queue or here being repaired. And another way is to apply the little machine, the little law. And another verification that I did in this case is I have the mean time between failures. I can compute it directly, and each time that here. Each time that a machine fails, I get the all the time passed divided by the numbers of machines that have failed. So I compute the time between one failure and another, disregarding which machine is the one that failed. And the other way is to take the theoretical mean time between failures of one machine, but I have to divide by the number of machines which are up, because if I have one machine, it will fail in about 60 hours. But if I have two, then each of them will fail it means in 60 hours, but it can fail one or the other. So the mean time between failures of the two will be the half of it, and so on and so forth, right? That is a hint of another way to model this, that is that you produce a machine each time that it fails, but it's more complicated. Okay, so I simulate, sorry, remove the real time, put the real time, and I have the machines that are here. Some are failed before, others will fail much later. Here they are being repaired. This is a way to show how many repairments I have at the moment. And okay, they go cycling. So maybe some machine is that failed is here again and will fail very quickly before the others have failed for the first time, and so on, right? The second example, or another of the examples that you had, is, I will stop this one or finish. And here, for instance, the check-ins that I said before, it says, applying the little law, it says that I have 7.6 machines down in the average, and here I have 5.6 repair persons in the average, so busy, so they are 5.6 machines being repaired in the average, and in the queue there are 2 plus 5, 6, 7, 6. It is okay. And again, the same. I have 25 less the machines that are down. It is 17 plus 0.4. So if I divide the 60 hours by this number, I get the mean time between failures, that is 3 hours and a half, which is the same that I have recorded counting, dividing the total time between the number of failures. So everything fits. Okay, so go with another one. The other one in the order of strange is the, oh, sorry. I would say that it is the car wash. The car wash, I have 5 booths where cars are being washed. They arrive, and if the booths are all busy, they have to wait in a queue, and otherwise they spend some time and so on. And this opens a number of hours. So there are things that are common to other examples. It's going to happen. My model here is cars arrive. I have a clock to open this because it is open 11 hours. After the 11 hours, I will close, and then I will wait for all the cars to finish. Then again, this could be an entity processor. I did the resource with get says resource and release, and then the statistics. The model is very simple in this case. Here they are working, and in this one, the many things are just the same as I explained before: the utilizations, the little law, and so on. And the new thing here is that they ask us which is the probability that one car finds all the booths busy, or which is the probability. Maybe this with the replications. Yeah, it is with the replications, so I stop it. Well, it doesn't matter. Sorry. The number of the part of the time that all the booths are busy, and I can do it in 2 ways. One way is just to observe this. That is which part of the time all are busy, and this is, let me stop here, is the times in which the number of are busy, all of them. divided by the complete time. And this is the part of the time in which all the booths were busy. And the other way is applying the pasta theorem. So what I do is, which is the probability that a car arrives and everything is busy, and how I compute this? The cars who find everything busy are the cars who had to wait. So what I compute is the time. Let me see, is this one? Final busy. It is, I count the cars that had to be waiting. So here I have a state waiting. So all the cars who were waiting are the cars who found all the states booths busy, and it gives me the probability. And as you see, is here is not the same because I am in the middle of a simulation, but let me do it fine. Remove the multiple runs that were for getting the results after lots of days. So if I do the simulation, it's not exact, but the direct way of seeing it is 71%. At the random observation of the arriving cars is 72%. That is very similar. Okay. And finally, the last exercise was the credit card operation, where we have a service department and it is open all day. And then customers arrive, they are attended by one person. Some of them are scaled to another specialist and so on. And I want to know the utilization of both workers, the average number of customers in each of the queues, the delays in the queues, and the probability that a caller is rejected. That is when there are many. I think well, there are 5 callers in the queue. If you have 5, you cannot attend, and so that customer has to abandon, right? And for that, the model is like this. There is something new in this case. Okay, I will explain that. Okay, it is quite, in this case, is one server for one, another server for the other, a branch with a probability you have to go there or not, then the statistics for the total time and so on. And the rejection is something that I do in the queue. In the queue, you can put a renege condition. The renege condition is something that has to happen, and when it happens, after some time, the customer or the entity will abandon the queue. And in this case, the condition is that the queue length is greater or equal than 5. So if you arrive here and there are already 5, and you will be the 6th, then you will abandon. In how much time? 0 seconds, immediately. So when you do that, then you are rejected. Okay. And here I count how many go here, and this is the reject probability. They ask me the probability that the queue is full. Is the same. The ones that are rejected are the ones that observed when they arrived that the queue was full. And the queue full, this is done directly. That is with the one of the two. Here, one of the two is with the, this one is with the which part of the time the number of customers in the queue was 5. So it's the true number, right? So here is the model. Everything else is, I think, it has appeared in other examples, right? Don't know. This was the idea. I hope of course, you were uploading your solutions up to now, nearly. So I hope you more or less could manage to make your models. Maybe some of the things were more difficult and you had some problems. Maybe with explanation now, you you see how to solve those things. So the idea is just to learn by doing, and maybe sometimes you know what to do, and in other cases you have to go to the manual or see another example and so on. At this point, I think it is good that you self-assess your work. I did that. This was the solution. Okay, this is okay. This was not, and so on. This is a good exercise. And then also now maybe it is a good time to when you have time to go to the other examples, the packaging line, the push-pull, and so on, that you have just to see more. When I do it in my classes with people, after this part, then I usually get one of these examples, I show it, explain more or less the idea that you have now in the statement, show my model a little, and then I leave the model for the students to just to play with it, to see how it is done, and to have it as an example for their models when they do their projects and so on. Okay, I think this is all I wanted to tell. I hope it was okay. Everything was okay? Any question? Reactions? Roberto was one, I think he was one of those that observed the number of students in the career mixer just when they were leaving. Probably it gives you a slightly larger number than the true number, because you just do it when you are still with the student, and then it will depart, but it should be very very approximate. Okay, so goodbye. See you.